All right. Now we're going to talk about a different type of circuit. This is going to be a Hamiltonian circuit. And it's named after Hamilton because when he was investigating dodecahedron, he was looking for, is there a way to create a circuit on a dodecahedron such that it contains no repeated edges and no repeated vertices? Could you create a circuit actually on this object that would achieve that? Where it would go to every corner of the dodecahedron and cover every single vertices of the dodecahedron, but never repeat itself. Okay, that was the question that he was asking about those things. And I'm going to explain some things about stellated dodecahedrons here in class because this happens to be a hobby of mine. And so, what we're going to do with this is a three-dimensional shape. We're going to try to turn it into a projection of this three-dimensional shape onto the plane. And we're going to look at it that way. Okay? So if I took the projection of the dodecahedron onto the plane, okay? Well, let me first write down this definition. I'll give you all a second to draw this picture right here. Okay, so if we look at the shape of the dodecahedron, there's 1, 2, 3, 4, 5 vertices on top. Okay, these vertices have to connect with 5 that go around the middle, another 5 to go around the middle, and then you have what? You have 5 vertices on the bottom of this thing. Okay? So, if I want to write this as a projection, include all the edges and everything, I get to this projection right here. And it won't zoom out any more than that. Okay. And now, a lot of y'all look at this and say, well, it looks like the vertices, the degree of all the vertices of this are odd, which is true, there are odd edges to this. But is it possible to create a Hamiltonian circuit that will actually, did I get one that hit up all the edges and all of the vertices? No. A simple circuit that includes every vertex of the graph. Okay, so what we won't want is we don't want any repeated edges, but we want to hit every vertex of this graph. Okay, so we're going to try to create a Hamiltonian circuit of this graph. And so a Hamiltonian circuit, what is this? The definition of this. Okay, would be a simple circuit Right, so let's go back to our definitions of what it means to be a simple circuit. So by our definitions that we put out earlier, the concept of a simple circuit, which is not in my notes anymore, is that it's closed. Okay, so one, this thing has to be closed. Okay. Second thing, has at least one edge. Okay. And then for it to be a circuit, it would have to have no repeated edges. Okay, so that's just from the concept of it being a circuit. Okay? The fact that it's simple means no repeated vertices. Okay, so what are the major differences between a Hamiltonian circuit and a Euler circuit? Okay, a Hamiltonian circuit says that it's a simple circuit that includes every vertex of the graph, so it has to include every vertex. And since it's a simple circuit, there's no repeated edges or no repeated vertices. But the difference between an Euler circuit and a Hamiltonian circuit, well, first of all, this one has no repeated vertices. Okay? What is the other difference that is between them is if we look at the definition of what an Euler circuit is, okay? So we say a simple circuit that includes every vertex of the graph. And an Euler circuit is a circuit that contains every vertex and every edge of the graph. So, what is missing out of this is that every edge part right there. Okay? So, with the Hamiltonian circuit, you don't have to include every single edge. Okay? But with both of the, and with the Euler circuit, you can also repeat a vertex. So when we were dealing with, where did that go? Like this one right here, this is Euler, and you hit a vertex more than once, okay? For a Hamiltonian circuit, you're not going to repeat any of the vertices, and you don't have to hit up every edge of the problem. But you do need every vertex. The other one required every vertex and every edge, but allowed for repeats of the vertices. Okay. So can I take a dodecahedron and actually create a Hamiltonian circuit on it? That becomes the question. Okay. Well, I'm going to take my projection okay, zoom out a bit. If you need to pause this and watch the video later, that's fine. Okay, so y'all see how I drew these dash marks on this thing? Is there a way that I can start going around this and actually get to every single vertex without repeating a vertex? What was the other condition? Okay. No repeated edges, no repeated vertices, and I have to hit every vertex. Okay, it doesn't mean I have to hit every edge necessarily. Okay. Well, is it possible to do this? If I just put it right on top? Yep, it's totally possible. So what did I do on this thing? I started off right here. I went into my innermost circle, and then I went down, and then I went into this circle. I covered everybody. You can think of this as the top of the dodecahedron. This is the top of the dodecahedron. And then the 10 that are associated with it are going to be the sides of it. And then this 1, 2, 3, 4, 5 that is in this big outer part right here, let's say the bottom. Okay? So I'm going to start at the bottom, and I'm just going to pick one of the vertices on the bottom. And then that's going to send me into this middle part. From that middle part, I can make a connection to another middle part. And then where does that put me? That puts me, now I'm at the top of the dodecahedron. And I can walk around the top, okay? And I can go back down to that middle row that goes around itself, make up all the connections of the middle row until I stop, because I don't want to hit that guy again, because you don't want any repeats, okay? And then what I do, I went all the way around the middle of the dodecahedron, and then I said, okay, now I'm going back towards the bottom, and to complete my Hamiltonian circuit, I go around the base of the dodecahedron, and that completes the circuit. I did not repeat any edges. I did not repeat any vertices. I covered every vertex, and it's not necessary to cover every edge, okay? An Euler circuit said you had to cover every edge and every vertex. This one, no, you don't have to cover every edge of it. So, this isn't like a subset of another set. There's a difference between an Euler circuit and a Hamiltonian circuit.